Hi, yeah, today we will talk about fossils. So let's get started. We'll first talk about the formation of fossils, and then we'll discuss the applications of fossils in stratigraphy. Uh, we will briefly talk about marine ecosystems, and then we'll talk about how fossils uh, can be used to study paleoclimates. We'll look at a few examples. So, the most voluminous part of our discussion will be about the fossil formation. So then, what are fossils? Fossils are the remains or traces of ancient life, which have been preserved by natural causes in the Earth's crust. So then, the life forms that lived at the surface will eventually can be preserved as fossils. However, they need to go through several changes, and this process takes a pretty long time. However, we did find fossils of several different organisms preserved in mostly sedimentary rocks. Then, what are these fossils? They can be bones or shells, that is, hard parts of organisms, or in general terms, remains of organisms. Or they can also be the traces of organisms. When we say traces, any interaction between the animal or the life form and the host material, which is mostly the sedimentary rock material. Any interaction between the organism and the host rock material, if it is preserved, then that's a trace fossil. So, which includes the track marks, trail marks, burrows, grazing, nesting, and anything related to that. The organisms' living conditions during which the organism interacted with the sediment, and if it is preserved, that interaction is a trace fossil. And in these two photographs, I took these photographs when I went to the Dinosaur Valley State Park in Texas near Dallas. You can see examples for dinosaur tracks, two different, made by two different dinosaur group species, right? Then, under what conditions do the organisms uh, get preserved eventually in future as fossils? What are the required um, geological uh, scenario, right? What is it? We'll talk about that on the slide. To become preserved as a fossil, an organism must first of all um, uh, uh, contain preservable parts in the body. When we say preservable, we we referring to some hard part that eventually can be fossilized and be found. Mm. So these conditions are true for to find a fossil, made of hard parts of the organism, right? And then these hard parts need to be buried by a sediment, and this is required because otherwise, if it is exposed to the elements, they may undergo mechanical decay, right, and disintegrate, or um, uh, they can undergo decomposition and then decay. So then the organism's body need to escape physical, chemical, and biological destruction, right? Before and even after it gets buried by the sediment. Uh, to accomplish all this, the best suitable environment is ocean, of course, because when the organism dies in the ocean, its body is buried to the uh, it sinks to the bottom of the ocean, and there it gets quickly covered. It has a good chances of getting covered by a sediment layer, and then eventually these conditions increase the probability of that organism in becoming a fossil. So these are some required conditions for uh, for fossilization, right? The burial of the organism's body with suitable parts that can be fossilized under a layer of sediment, and then before and after the burial, the organism's body need to escape disintegration, right? And the best suitable environments are for fossilization are ocean or near ocean environments. Now, we'll talk about different types of preservation um, that lead to the formation of fossils. First, we'll talk about preservation of unaltered hard parts. We do find hard parts in their unaltered conditions. For good examples for these can be bivalves, for example, the types of shells you will find in the nearshore environments, right? Or snails, or corals, right? In addition, you may find oyster shells, shells of foraminifera organisms, echinoderms, that is, this group includes sand dollar making organisms. So these are some examples for fossils that are made of unaltered hard parts, right? And the composition of such unaltered hard parts can be phosphates, silica, or sometimes organic matter such as pollen grains have a chance to be preserved as unaltered hard parts, or entire body of an insect if it is caught in amber, for example, right? So we did find in the rock layers the type of fossils that are made of unaltered hard parts. Very frequently, though, we find the bodies of organisms altered, especially the hard parts that have a higher chance of getting preserved as fossils. We find them in their altered state. The processes that bring in these changes to the hard parts after their burial and during the fossilization process include mineralization, replacement, recrystallization, carbonization. These are some example processes. In mineralization, if there are pore spaces in the hard part of the body, like for example a bone, dinosaur bone, for example, right? These tiny pores can be filled with sediment deposited by percolating waters that percolate through the sediment that actually buried and the hard part. So these waters can go into these pore spaces and deposit chemicals such as silica, phosphate, pyrite. These are some good examples. And as a result, the original hard part, right, gets modified or altered. Another process that can accomplish the alteration of hard parts is replacement. Here, one mineral replaces for another, and this can happen at molecule by molecule scale, so at a very minute scale. As a result, original structures and textural features can get preserved. So that's replacement. And usually silica or pyrite are seen replacing the original material that can be calcite. During the burial of the sediment, the fossil materials can get recrystallized. Good example for this process altering the hard parts is the shells that were originally composed of aragonite. It's a mineral, calcium carbonate, recrystallizing into calcite, right, which is again calcium carbonate, but aragonite and calcium calcite, they are two different, indicate two different minerals, right, composed of same composition. Or during recrystallization process, amorphous silica can crystallize into its mineral form, is quartz. Carbonization is another process that alters the hard parts. During carbonization, soft tissues, the living tissues, undergo changes during which carbon is retained and the remaining chemical components are removed. So at the end of carbonization, only a thin carbon film is preserved as a fossil. Right? So a good example for this kind of fossilization can be leaves of fern getting carbonized and leaving a thin, shiny film of carbonized material. So these are some examples for alterations the hard parts can undergo during the fossilization process. So first we talked about altered hard parts, then we talked about unaltered hard parts. Fossils can also be preserved as imprints, during which molds or casts may form. A mold is a void in the sediment left by a dissolved shell. So when the sediment covers a hard part like a shell, for example, and then later if the shell dissolves, that leaves an opening in the sediment, and that's the mold. And if this opening is filled later with the chemical material by precipitation, then we call that as cast. So these types of fossils are imprints. Very rarely, though, organisms can be preserved as unaltered soft parts. But such a preservation requires special conditions such as freezing, or in the arid climates, desiccation, or if the organism is caught inside, like insect inside amber, or larger organisms' bodies caught in tar. So any natural process or setting that prevents decomposition of tissues may lead to the formation of a fossil composed of unaltered hard parts, right? So we see some examples for those conditions listed on this slide. You can see some examples for unaltered hard parts. Right here, you see body of a mammoth that was 44,000 years old. So that many years ago, this mammoth was a living organism, and we found a fossil of this mammoth as an unaltered soft tissue preserved in the permafrost of Siberia. So when the permafrost melted, this fossil was exposed. And what we see here is a Eocene age insect, so that is tens of millions of year old insect, but you can see it is well preserved inside amber. And this is half of the body of 2,000 year old man, right? Found in peat bog, right? Peat bog indicates a swamp environment. And of course, we talked about the trace fossils at the beginning on the first slide. Organisms can also be preserved as trace fossils or ichnofossils, in which case there is no hard part preserved or any soft part preserved. It is just trace fossil or ichnofossils is a fossil made of the um, is a fossil that recorded any type of interaction between the organism and the sediment that hosted the organism's fossil. So the good examples for these are tracks, trails, burrows, borings, root marks, nests, eggs, coprolites or fossilized fecal materials, or bite marks. So there are several different types of trace fossils. Here you see the first figure here showing crawling traces, resting traces, dwelling traces, grazing traces, and feeding traces. And here we see worm trails preserved well in 300 million year old siltstone from Ireland. And here you see dinosaur tracks, right? I've shown you two photographs with dinosaur track trace fossils on two of the previous slides, right? And these are worm burrows, again in 320 to 350 million year old siltstone from Missouri, USA. So these are all examples for trace fossils. Trace fossils can give very important information about past environments where the organism lived, such as water depths, water currents, availability of food, how fast the sediment was deposited. The tracks provide information about foot structure, the number of legs, walking speed or running speed, and related behaviors. So there is even though there is no hard part or soft part preserved in a trace fossil, the biological information, a lot of it is preserved in them. So there it is. So that's about fossilization and some example processes and also about the types of fossils, right? Now let's see how fossils are useful in stratigraphy. Now, to be useful as a age indicators, fossils require to have certain characteristics, and they need to be found in the rock layers that are being studied. From there, one needs to know the ranges, time ranges for the fossils found in the rock layers, and one needs to see if any of them can be useful as an index fossil, which indicates a particular interval of time during the geological past. So one needs all this information to use fossil information to find the age of a particular rock layer. So here we have an example, right? We have fossil X, fossil Y, fossil Z, right? Taken as examples. So these three figures are providing some information, right? And these are the ranges of those three fossils, right? For example, X, the range of X, the first appearance and the last appearance of this particular species starts from Cambrian, Ordovician, and Silurian, right? Whereas the Y, the range of Y goes from Silurian, right, to Devonian, right? And range for Z starts in Devonian, and of course it goes into Mississippian, right? So there it is, we have ranges there, and then we can apply that knowledge to this rock layer to figure out the age, right? So there can be only a specific time interval that these rock formations belong to, because if you look at this, for a rock layer to have these two, to host these two, it must have lived, it must have gotten deposited when these two were living together, which is according to this Silurian, right? So fossils can be useful like that, but you can see one needs additional information before one can use fossil data, right? Stratigraphic studies. So these are this slide gives us ranges of different groups of invertebrate organisms, such as Sarcodina, Porifera, the sponges, Cnidaria, corals belong to this group, bryozoans, brachiopods, mollusks such as gastropods, bivalves, cephalopods, arthropodians like trilobites, right? And let's see, and some other echinoids like echinodermal organisms and so on. So here you see the first appearance and last appearance for these organisms, and you can see these colored areas are where they are particularly useful as time indicators. So if an organism lived on several different continents, that is widely distributed, but lived only over a very short geological range, that is first appearance and last appearance during the geological time is the range. And if an organism has a very short geological range, but during that short time period when it existed, lived, thrived, if it lived or if it is widely distributed, then one can use that particular fossils of the particular organisms as index fossils, because presence of them indicates a particular interval of time in the geological, right, chronology. So we have some examples here. Ammonites were particularly abundant during Mesozoic, but they went extinct at the end of Mesozoic. So that's the presence of ammonites may indicate a particular interval of time. Likewise, graptolites. So you see an example of ammonite here. These are graptolites. They thrived from Cambrian to early to mid Carboniferous. So at the end of which they went extinct. So the presence of the fossils of graptolites, right, indicates Paleozoic age, and especially between Cambrian and Carboniferous. Trilobites, these are arthropods. They appeared during early Paleozoic. They became extinct in Permian. So likewise, Physalinid, Foraminifera, they went extinct in late Paleozoic. So you have some examples for fossils being useful as particular time indicators, and you have some examples for index fossils on this slide. So for each period, right, these particular organisms, species, are useful as index fossils, right? For example, Paradoxite spinus, this is a trilobite. Likewise, Prophytis subbulacus, that's ammonite, and And likewise, you see some additional examples for our pecten gibbous, that's bivalve, Calyptra fortis, vellatus, that appears like a gastropod. So these are some examples for index fossils, and they are given for each period, right? So their fossils are very useful in determining the relative time, and if appropriate fossils are available in the specific time interval. Then what other information can fossils reveal? They can tell us about marine ecosystems, or the ecosystems that were in which this organism was a part when it lived. And that's because the organisms that live in different marine ecosystems, they have specific. In other words, they live in based on the type of species or fossil assemblages found in rocks. A particular ecosystem that was present can be identified. So first, let's look at the marine ecosystem divisions, and then we'll look at some information related to the fossils. So in this figure, the marine ecosystem divisions are shown. The two main areas can be the ocean floor environment, right here, and the water environment, which lies above the ocean floor. You can see the ocean floor environment can be divided into littoral, sublittoral, bathyal, abyssal, hadal. Hadal, the deepest parts of the marine environments. Abyssal are deep, but hadal are the deepest. And then the water area, the water column above the ocean floor, that's the pelagic rhyolite, right? So ocean floor rhyolite is the benthic, and the water pelagic rhyolite. And the pelagic rhyolite can be divided into intertidal, muriatic, and oceanic, right, environment. And then organisms, based on the modes of life, can be divided into planktons, which are floaters, nectons, which are swimmers, or benthics, which are bottom dwellers. So the benthic organisms tend to live at or near the ocean and ocean floor. So planktons are floaters. Some are plant-like organisms which photosynthesize, includes diatoms, coccolithophores, or some are animal-like planktons, foraminifera, radiolarians, tiny mollusks, small crustaceans, are some good examples for animal-like floaters. So these are big swimmers. And then you have nectons, which are good at swimming. Good examples are squids, nautiloids, jellyfish. These are invertebrates without the vertebral, without the notochord. Vertebrate organisms that are good swimmers include fish, whales, and then some marine reptiles. And the bottom dwellers, the benthic organisms, include organisms such as clams, sand dollars, worms, um, which live beneath the sediment layer at the ocean floor, so that they are informal. And some like algae, sponges, coral, brachiopods, crinoids, blastoids, they are epifaunal, that is, they live on top of the sediment surface, right? So so that's about benthic organisms and the necton organisms and planktonic organisms, right? Now, one also may find sediment covering the ocean floor, and some of the sediment is biogenous, that is made of biological material, and that biological sediment can be a calcareous ooze, which is made of shells of these organisms, foraminiferans, pteropods, and coccolithopods. Or it can be, the biogenous sediment can be siliceous ooze, um, made of shells of these, including these organisms, radiolarians, diatoms, or materials such as fish bones, teeth, or fish scales may be found in the biogenous sediment, in which case they are made of phosphatic material. Right? But you also will find on the ocean floor terrigenous sediment, which is made of weathered rocks, or hydrogenous sediment that got precipitated directly from the ocean water. So that's something about marine ecosystems. So since the type of organisms that live at different depths um, changes, so the fossil assemblages tell us about the ancient marine ecosystems, which eventually help us to decipher the Earth's history. And what about paleoclimates? Well, we found pollen grains, for example, in the fossil record. Pollen grains are, the, are derived from plants, as we know them. So then plants that live at different climates have different characteristics. So if one can identify the type of plant that produced a particular type of pollen grain, um, then these pollen grains indicate us about the climates that thrived or that were existent when the plants that produced a particular pollen grain fossil lived. Right? Likewise, if if the fossil that was found in limestone, for example, was a coral, was made by a coral, then we know that for the corals to grow, they require a shallow marine environment. They need warm ocean, warm waters. They need clear water. They also need particular latitudinal conditions, that is tropical latitudes. Only there, the ocean waters are warm, and also um, for the shallow waters, the environment needs to be shallow sea, that is a continental shelf, for example, um, and uh, and also it needs to be shallow because these organisms require sunlight as a part of the growth process. Right? Coral building processes require sunlight, um, and for the same reason, it got to be clear water because muddy waters block the sunlight. So there, another example fossil that has information about paleoclimate can be coral, which indicates a tropical climate. So then there it is. We talked about several aspects of fossils that we found in a rock record. First, we discussed about fossil formation, the processes that lead to the formation of fossils, and then we talked about um, the applications of fossils in stratigraphy. And then we talked about marine ecosystems and the use of fossils in finding a particular ecosystem as an indicator of a particular ecosystem, and also about as an indicator of a particular past climate or Perlear climate. So that's all what I wanted to discuss today. And bye bye.